Hey guys, so here are the guided notes for 4.8, and I feel like I should apologize because I just rewatched the beginning of the last video and I said so many times. So sorry about that. It is what it is. Anyway, the top of these guided notes, this section here is kind of neat because it really gives a good sort of sense of the difference between a zero, a factor, a solution, and an x-intercept. And I shouldn't really say, that they're different necessarily, but they're all so similarly, they're also related and they're also similar, and the context in which we might use one word instead of the other, changes. So this, I think, does a nice job sort of saying, okay, a zero is this, a factor is this, a solution is this, an x-intercept is this, okay? So I would definitely highlight this or somehow sort of earmark this little section here because I do think it's really relevant. Moving on, we're going to do a couple examples together. In this section, I really like. This section is on analyzing graphs. So what we're doing now is we're sketching higher degree polynomials based on the information that we can garner from the form that they're given in. So right here we have two functions, and at first they might look like quadratics because we have a term being squared, but you need to also recognize that the term beforehand has an x in it as well. So altogether we have two x's here, an x here, so this is a cubic. And in fact, both of these are cubic. So we know that these are cubic functions. It's really good to get a sense of this guy's positive, this is positive, they're probably going to look like this. Oftentimes when we have a cubic, or I probably should say all the time that we have a cubic that doesn't have this sort of n look to it, maybe where it just has this inflection point, is when we have a multiplicity of 3. So that is not what we're dealing with here, because we see we have at least two distinct roots, and then this root has a multiplicity because it's being squared. So that factor gives us an x-intercept, which is a solution if we're solving for x when the output, the y, is a 0. So to graph this guy, first what I'm looking at is, if I want to graph just the intercepts here, then I would set y equal to 0. And I would solve for x. Now, if I were to multiply both sides by 6 to get rid of this, it's not going to affect the 0, right? So that doesn't affect my roots. This only affects the stretch or shrink sort of above and below the roots, but the roots are anchored on the x-axis regardless of the stretch or shrink. So here I have a root, or an x-intercept of x equals -3, and here x is 2, and that has a multiplicity of 2. So what I'm going to do is I'm going to graph this point where x is 2 right here, and graph this point where x is -3, and I know that I have a multiplicity here of 2. So if I think about this cubic and the root on the right has a multiplicity of 2, it can't be this turning point because then I wouldn't have another x-intercept to the left. It must be this turning point. So before I do anything else, I'm going to sort of do one of these and just recognize I have a turning point here, and from here I'm going to go straight down. Okay. And the other thing I want to look at is the fact that I have a vertical shrink by a factor of 1/6. So another thing that's really nice to have here is a sense of what's my y-intercept. Okay. So in order to find that, I can think about if I were to square this term here, the last term would be a +4, right? So a -2 times a -2 is +4. I'd have a middle term and a leading term as well, but at the very end I'd get a +4. Then at the very end here I have a 3, so that would be 12. And then times a 6 would give me 2. So I know that my y-intercept is 0, 2. I can also find that just by plugging in some 0. So 0 minus 2, -2 squared, 0 plus 3, 3, and then a 6. So essentially the same math, just kind of thought about in a different sort of way. So I have a y-intercept right here. So right now I have these 3 points, and that's pretty much enough to get a pretty decent sketch of this function. So I'm going to fill this in just like that. Now this guy might come up a little higher. If I wanted to get a better sense of what's going on in here, I could maybe plug in a -1 and just sort of see where that guy lands. So if I were to do that, -1 plus 3 is 2. -1 minus 2 is negative 3 squared is 9. So this would be 2 over 6, which is a third of 9 is 3. So that gives me a little bit more information. So I know that at least I'm hitting up here, okay? And I don't know that that's like the turning point per se, but again, that gives me a little bit more information to sketch a pretty decent graph of this cubic function. And I want to make sure I make it look like a cubic and not like it's got too many angles in it. I should have lots of curves. So that would be a pretty decent sketch of that function. Over here, same thing, and I'm going to go through this one a lot faster. So my roots would be at negative 3 with a multiplicity of 2, 2. My y-intercept would be 9 times negative 2, negative 18. Let's make sure I get this right. 9 times negative 2, negative 18 times a fourth. Ooh, that doesn't come out super nice. That's okay. So negative 18 fourths. So let's see. That would be negative 4.5 roughly. So my y-intercept should be about here. And then if I sketch my roots at negative 3 with the multiplicity of 2 and 2. Now, even though this function is still positive, but because the multiplicity is on the left, that sort of relative maximum point is going to hit about there instead. So this would probably be a pretty decent sketch of this graph, okay? And again, we could plug in a value in between here. Oh boy, that was not nice. To get a better shape if we wanted. So we could maybe, because I'm kind of treating this like this y-intercept is a turning point, and it's not necessarily. So one thing I can do is I could plug in, let's say, a 1 and just kind of see where this guy goes. If I plug in a 1, I've got negative 1 times a fourth times 4 squared. So 16 times a fourth is 4 times negative 1 is negative 4. So I plug in a 1, I get out a negative 4. Okay, that looks good. That helps me out just a little bit. So I'm going to say that's good enough.